All right, hi everyone. I got to correct two pieces of misinformation that I spread earlier this week. Sorry about that. So one, the drop deadline is like nowhere near soon. Actually, I might have said that it is on Monday. It is on a Monday, but not next Monday. The other is that I claimed that there was a piece of code on the mid where the answer was that it doesn't crash. There was not. They all crashed. So yeah. Okay. The answer to question whatever. So the answer to all of those is that there is problems. So yeah. So okay. Like I thought I put in one where there wasn't, but that was not the situation. Okay, since that got people excited, why don't we go through it and see? So okay, so yeah. So this one is problematic. Why? Anyone? Yeah. That's correct. So this is a string literal, even though that's the scar star that will compile. However, you try to modify it. That's undefined behavior. You're not allowed to modify something that was defined as a string literal. This is a problem. Why? That's an easy one. Out of bounds, exactly. Yes. So this is like element number 4 of a block of 3. This is a problem. Why? It was someone else. Yeah. Yes. Yeah, we freed it, not allowed to access memory that's been freed. That is undefined behavior. This is a problem. Why? Yeah, you said, yeah. That's right. So we're trying to write 6 things into space that only has 5. This is a problem. Why? You only initialize the block of like pointers that's right. That's right. So block at 0 is legit. That's element number at index 0 of block. But block at 0 is an address that's not a valid address. So you try to access something there. It's grade is not there, like nothing is there. It's a pointer that's just a random, not initialized. So block at 0 is a value. That value is an address, but that's a random address, not an address where you can say, go to the student there. That doesn't, yeah.
Do we have to provide all possible reasons, or is one reason?
One is enough. If you see another reason, that's a time too, if it's a valid reason. Yeah. So the concept there was like you can't really explain why something is not a problem, because like not a problem just means it runs. So and then yeah, like you find another problem, that's fine too. Okay, all right. So that is now corrected. So we are back. So in this half of the course, it starts to be that there is a lot of code. So there is a trade-off between just kind of watching and not writing. Sorry, this is stuck. Okay. So there's a trade-off between kind of watching and not writing. So today I'm not actually writing like all that much code, but I am, well, I don't know what's going on. Hold on. So I just want to show you where the code that I'm about to write is. And it doesn't click. Okay, it's fine here. Yeah, so I posted like the draft lecture 21 over here. So you can, I think a correct workflow here is to find the place in the notes that I'm working on, then copy and paste it. And then if we kind of in answer to questions or whatever, we modify it, then you modify it on your laptop. I think that's one way of going about it. So, okay. So I want to actually start with a different thing. So we briefly said what a stack and a queue is. I want to re-implement those in Python just as a kind of practice. So, all right. So this will be stack. So first of all, so a stack is an abstract data type. So that means that it's like a mathematical thing that's not necessarily tied to any particular implementation in Python or in C or whatever. So a stack is an ordered collection with the operations push and pop and is empty. Right. And the idea is that you, let's say 6, it's like this. You push 7, it's like this. You push 7, it's like this. And then you pop by removing the last element that you pushed. So if you do 1 pop, that will be 7, and the stack is now 6, 7. And then if you pop again, it's going to be again 7, and the stack is going to be 6. And then you pop again, and the output is 6, and the stack is empty. Okay, so just so that we're not misleading about it, I'll put like empty with the reference operators so that you understand that that's just a symbol. Okay? Does that make sense to everyone? Sorry. So the way we want to be able to use it say if name is equal to main, is by saying, okay, I want to be able to initialize my stack like so, and then I want to be able to push and pop. So I want to be able to say, like push. So if I want to build 6, 7, 7, how would they build it? By pushing. So I want for it to be 6, 7, 7, so that when they pop once it's 7, pop again at 7, pop again at 6. Yeah. Yeah, someone over there. No? Well, I know that you know, so I'm not going to ask. So if I want it to be 6, 7, 7, I got to push it from the back, right? So I'll push 6. I'll push 7. And I'll push 7. And then if I pop, then this would be 7. And then again, the second one is 7, and then the second one is 6. And then is empty now is supposed to be true. And otherwise it would be false. Okay, so that is how I want to be able to use it. Does that make sense? So what we had done when we did it a couple weeks back is we said, well, this is basically just a list to which you append and from which you pop. So pop in Python gets you the last element of a list and removes it. That's exactly what we want, right? So here I'm basically going to be re-implementing that just so that I'm able to say dot push and dot pop like so, right? So again, the strategy is inside of our stack, we'll actually say, okay, that's actually a list for now. So, all right, I'll say class stack. So my init don't even really need it because it doesn't do anything, but I can do it. If you leave it out, that's also fine. And now, sorry, so I do need to say, yeah, sorry, that was a mistake. So I do need to say that my L, or let's call it the data now, is empty. Does that make sense? And now I'm just going to implement my push and pop. So the push and the pop are going to just operate on this list data. Right? So push is going to be self. And that needs an element. So that's going to append the element to data. And then pop is going to return data pop element. So this is just not a general thing. It's just something that happens to work with Python lists, right? Didn't say self. So that's just because, like, if you say whatever, like L is 456, you can say E is equal to L.pop, like so. And L is now this, and E is now this. It just happens that the Python lists, kind of inspired by the terminology of stacks, use the pop function as well, right? So that's a coincidence. So this is not called push, it's called append, whatever. And this is, of course, like this. Does that make sense? So we're just gonna quickly test it. Okay, for some reason, it doesn't want to push any buttons here. Sorry, I'll stop sharing for a second. I think that's gonna do it. Yeah. Okay, so this is like this. I did not implement is empty, although it did output what I wanted. So 776. So is empty is, of course, going to be just return true if the length is 0. Don't return true if it's not 0. So that's going to be return self.data, the length of is 0. So now it's going to be is empty. You could call is empty elsewhere as well. All right, so that looks like this. Okay, does that make sense to everyone? Questions? All right, so I want to emphasize, especially if you didn't look at the lecture from last time. So what's the self thing about? It's just the Python way of making things like this look nicer, right? So you can think of it, and it does actually work as just saying stack dot push S6, right? So that actually would work if you run it. It's the same, right? So you're just calling this function. And what that does is it says s.data dot append ln, right? So the s just gets passed to self. Is that making sense? All right. So let's now, for the sake of the exercise, implement a queue. So you might ask, like, why are we doing stacks and queues? That does not seem useful. You would be correct as of right now. Those are not extremely useful things For now, they will be useful around week 10. They're also useful as examples. Okay. So a queue spelled like this, kind of difficult. So ordered collection, by the way, and ordered collection. So with the operations, so you could name those push and pop as well. Usually people call those unqueue and dequeue instead. And the principle is first in, first out. So a queue, or like North American English, more ordinarily a line. So like if you line up at the grocery store, the first person who lines up is the first person who gets served. That's what a queue is, right? So the first element that's unqueued should be also the first element that's dequeued. That's as opposed to this a stack, which is usually referred to as last in, first out. And people do an acronym as well. Right. So I mean, you can like remember it by the acronyms. I think some people find it useful. I just think about it as like a stack is like a stack of objects and you pop off the top. And then a queue is like a line at the grocery store. So, okay. So what should we do differently here? Just copy and paste this. Well, so with a stack, we had this very convenient thing where we can append and pop, and that just works as a stack. With a queue, that does not quite work. So we need to kind of like rethink that. So one possibility is you say, I want to keep this, but then I got to make sure that when I append or when I unqueue on the other side of the list. The other thing you can do is the other way. It's like you take from the beginning, but you append at the end. So you get to keep either the append or the pop. You cannot keep both. Does that make sense? So, in Python, again, you can actually pass an argument to pop. So if this is 5, 6, 7, say L pop 0, that pops the 5. So from position 0, and the L becomes 6, 7. So that's the convenient thing to do. It's like instead of saying pop, you say pop 0. And we'll rename those to unqueue and dequeue. Does that make sense? So we still maintain the data as a list. It's just that we dequeue from the beginning of the list and we unqueue to the end. So we always dequeue the element that's at position 0. Is that all right? Or like, does that not make sense to someone? All right. So if we do so we again on Q6, on Q7, on Q7. So I'll just change that. So I'm defining my queue, and then I want to unqueue 6, 7, 7. So that's like this, and then we'll dequeue. So if I dequeue now, what they'll get is the 6 because the 6 is what got unqueued first, right? So the pop got me 776 from the end. Here we get the thing from the beginning. And then we'll get the 2 7s. We can verify that that works. Invalid syntax. Oh, okay. And we got 677. So the elements that we unqueued in the order that we unqueued them. Is that cool? All right. So almost done with this. And we are about to move to implementing linked lists. There is like a nice story about why you would want to do it, which is that both the stack and the queue operations are potentially not all of one, right? So this is a little bit obscured by the neat Python implementation, but underneath the Python array is basically an array list. So the kind of thing that we implemented in C. So that means that all the elements are stored contiguously in memory. And that means that it might be that at some point you need to relocate your entire data list somewhere else if you append too much, right? So this implies that the push is worst case O of n. Because might need to move self.data somewhere else. And if self.data is of length n, then it takes O of n time to move it somewhere else in memory where there is space to append another element. Make sense? So that's like this. The way we implemented the queue, that has even more problems. So this is O of n every time. Is O of n, right? And that's because at least kind of the way it's implemented, you can fix it. But the way it's implemented, you got to move all the elements one space to the left, right? This is also worst case O of n. Does that make sense? So the O of n here is like a little bit fake. Like, yeah, like sometimes you would need to reallocate, but that's like not the usual situation. Ordinarily, what people say is, well, like it's like worst case O of n, but amortized over the lifetime of usage, it's O of 1. So the word is amortized. How many people know the word amortized? Just like from clearly you haven't taken out a mortgage. So amortized is like the average cost over multiple years. People say basically like the amortized cost is this much. So sometimes it would be referred to, it would refer to kind of the mortgage payments over the lifetime of when you pay them divided by, you know, the number of payments that you make, something like that. Right? Or like sometimes you buy something and it costs like a certain amount, but you're going to use it for 5 years or whatever. And then you would say, well, like I paid this much, amortized over 5 years of the lifetime of the device or whatever, it cost me this much per month. So that's what amortized means. So It's like approximately 1. Of course, like if we're talking about amortized, like there isn't even an M there, right? It's like average over how much you use the data structure, push and pop. Does that make sense? So in order to actually compute this, you might need to do somewhat difficult math because you need to actually model like what's your usage of the data, stuff like that, depending on how you use it and like what's the distribution of the kind of inputs that you have, it might be different, right? But in general, it's like approximately 1. Does that make sense? So it should make sense, except to the extent that actually, depending on how you use it, it might be different, and the calculation would be difficult. We're just not doing the calculation. We're just saying you would need to reallocate it pretty rarely, so it doesn't cost that much. Okay. All right. So that's the story. And then the idea is, well, if we were to implement it with a linked list, that would potentially be cheap because with a linked list, you can just say, I'm going to take up one node from the left. That doesn't cost me much. That's the constant time operation. I can take a node from the right. That also doesn't cost me much. That's just a node one operation as well. So if I had a linked list implementation, I could use that instead of using an array. And that would be a genuine O1 cost operation. So that's the motivation for what we're doing. It's all kind of for the sake of the exercise. So all right. So this is going to be linked list dot py. So we are going to do it basically the same way we're doing it in C. It's going to be easier than in C in some ways because there's not like choices about address of an asterisk and stuff like that because those things are still consistent in Python. So to the extent it works without the pointer math. So, all right. So we'll define a node. So the init is going to take self. It's going to take data. I'm going to say self.data is equal to data. So a node in a linked list also has a next. So Python does not have a null thing. Usually what people do is they use none. So none is not really zero. None is its own special object in Python, right? But there is no kind of null. So null in C is really just secretly a 0. None in Python is not secretly a 0. A 0 is a separate thing. But people kind of use it as the universal placeholder. All right. So we are going to do it like that. Don't really need anything else. That's what we need from a node is to have data and to have none. So we're going to now define a linked list. So it's going to have a head that's initially just none. And it's going to have a size, which initially is 0. Make sense? All right. So now we want to be able to append to the linked list, stuff like that. So the append is going to take some data. So append means append to the end, right? So at least kind of the way we're implementing it right now, it's going to have to be that we start at the head, we go to the very end of the linked list, and we append at the end of the linked list. Okay. So the way we're going to do it, so we're going to say, okay, so current is self head. So same thing as in C, right? So like self head would be the first node. And now we're going to say while current next. So I can say not equal to none. I can also say while current next. So that is also possible. And that's because even though none is not zero, none does convert to false in Python. Right. So that is maybe more explicit. Like so. So we are now, so now cur is the last node in the list. So we can now just say, okay, so current next used to be none because that was the last element. We can now just say current next is node data. So that creates a new node and we just stick it in next. Or rather we stick its address in next, right? So in C, what we did is we wrote it with kind of two lines, right? So you'd say n is node data, where n would be like the pointer, and then you would say cur next is n. That's of course the same, right? It's just that in C, we in Python, and depending on how you write it in C as well, you can just say node data, and that returns the address of the newly created node. Does that make sense? All right, and that would append. So we can also say like get I. So get element at index I. And here you would say, okay, so go through the list IND times and get me the data at there. So I would say like for I in range. And we just say current is cur next. And we return current data. Is that making sense? So if you wanted to be really fancy about it, you can say, okay, I actually want to use square brackets in order to do this. So this would be get item. Does that make sense? So I just renamed it so that they can use square brackets for it. Is this good? All right. So let's now progress. So what I wanted is I wanted to say I want to use my linked list in order to use stacks and queues with the linked list instead of the Python list. So the idea would be like this. So let's say I have a list like this. So if it's a stack, then what I probably want to do is I want to just say, okay, I want to be able to remove element 0. And I want to be able to kind of insert element 0. So I insert from the same end. And that's just how I do it. If it's a queue, so probably what I want to be able to do is I want to be able to append at the end at small cost. And I also want to be able to take elements out from the front at small cost. So operating at the end is easy, but if you want to be able to also append cheaply, you got to just remember where the tail is as well as where the head is. Right? So if I keep track of where my last element is, I can append really easily. Does that make sense? So I'll just do that. I'll just say, okay, so self tail is none. So this would be the last node in the linked list. All right. So I'll do just like custom operations here. I decided to do that now, which are append at the end, prepend at the beginning, push from the end, pop from the end, pop from the beginning. Right. So I'll do just like this quick and dirty rather than implementing the slightly more complicated pointer stuff where you need to rewire the linked list in the middle. So I'm going to say, sorry, this is not what's in the notes. I changed my mind. So I'm going to say append at start, I guess prepend. And I'm going to redo my append. And I'm going to say pop head. And I'm going to say pop tail. Actually, I'm not going to pop tail because that's difficult to do. So just those. All right. So how do I do prepend? So what does prepend mean? I have a thing that's like this. And I want to add a 6 at the front. Right? How do I do that? Well, I'll just say, okay, so first of all, I'm going to create the new node. And now I want for n to be the new head. And I want for the new head next to be the old head. So I'll say n.next is the old head. And now I'm going to say the old head is, the actual head is n. Does that make sense? So I'm creating the new node. So the situation is like this. If I'm prepending the 6, then I'm saying I'm going to connect the 6 to the old head. So it becomes like this. And then I'm going to say, well, actually, the head is now this 6. Does that make sense? All right. And then I'm keeping track of the size. So I'll say size plus equals 1. There is no plus plus in Python. It has to be plus equals 1. Cool. All right. So this is append. If I keep track of my tail, then appending is super easy. I'm just going to say self tail next is the new node. And I'm going to say self tail is n. And I also need to hook up. I already did hook it up. So this is the hooking up. And this is the keeping track of where the tail is. And again, I'm going to add 1 to size. Make sense? So we got to take care of the special case where the thing is empty. So in both situations, I need to create this guy either way. But if there is only a head, then I'll just say so this works either way. Oh, this actually works either way because this is fine. This is just none. This is none. This is plus equals 1. So that's fine. So the prepend works either way. Here, the append is not going to work because if self.tail is none, then self.tail does not have a next. Right? So I'm going to say if self.tail is not none, then it's like this. If it is, then we got to also initialize the head to be the same. And either way, self.tail is n, and the size increases by 1. All right? So we have the append and we have the prepend. And now pop head is just saying, get me the value at head and remove the head. Right? So the data is going to be self-head data. And now self-head is going to be self-head next. And we return the date. Is this good with everyone? Yeah, everyone? All right. So that does it. Let's test it a little bit. So we're going to say, so LL is going to be like linked list. So again, to remind you, class linked list, the init runs. So what's going to happen is ll.head becomes none, ll.tail becomes none, and ll.size is 0 initially. Does that make sense? So now what we can do is we can whatever, like append okay, we'll append 6 and we'll append 7 as one does. me try to see that it actually runs. Okay, it did not complain. So now we got to look and see kind of what's inside. We could print those things one by one. We might as well just create a string that displays what the linked list is like. So if you remember, repr for representation is what runs when you try to print it. So by default, I don't think I did it last time. If you just say print LL, it's going to say it's an object of type linked list. Right? So that's not super useful. So that's like the default representation is an object of type linked list, and it's stored at this address. So here we're actually converting it to a string. So we're just going to say, okay, so result is like the empty string initially. And then we're going to keep adding like the data and then an arrow or something. So while, by the way, I forgot to decrease the size. So we're going to say while current is not none or something. So we're going to add current data plus like the arrow just to draw the linked list, right? So that's going to be like this. And we're going to advance current to be current next. So we're done. We return the result. If you want to be really nice about it, you might like to not add the last arrow. So I'm going to say, like if cur next is not none, then we do this. Otherwise, we just add like the current data, but not the arrow. Make sense? So we run this. So str, like this. And we got 6. All right. So we're out of time. So we'll quickly implement stack and queue in all one on Monday. I will see you. Thank you. Bye.